Let's do a logistic regression. These are the data I spoke about in class, namely we're trying to estimate the area of effect for cattle tanks on kangaroo rat populations. What happened in this data set was that there were 28 transects that were performed radiating out from the cattle tank. For each of these, the number of meters that were walked until a kangaroo rat mound was found was indicated. So you can look at the data set here directly below me. For example, the very first transect under R here, the kangaroo rat mound was found at 50 meters. There were a total of 28. So by the time you get to the 28th transect here, there you had to go 550 meters, but of course there, by the probability of finding a kangaroo rat mound was 1. So here's the probability of finding the kangaroo rat mound. This is a weighting variable, and I'll talk about that in a few moments. And then this is P prime, which is the transformed data. Those transformations and all these computations are given in the Excel file which accompany or which are embedded in this CSV file. So the first thing we do obviously is clear the memory, so rm list equals ls, and then I'm defining the data set as krat for kangaroo rat, so read.csv, and then I type in krat, and that then gives me this data set. Notice here this NA. NA is used to indicate a missing value in R, so unlike SAS where you would use a decimal point, here we're simply going to use NA. And this is a computed value right here, and this is not defined at this point. So this is the Logistic Transformation here, and you'll see how that's computed in the Excel file that accompanies this. So we attach that data set, and the first thing I do is I plot P prime, so that's my transform probability, against distance, and you'll see that graph here on the right hand side. All right, so there's the plot. There we go. And then the red line is indicated by this command AB line. So linear model P prime is a function of distance, and I specify that the line should be red. I then pull up ggplot and do the same thing, plot the line, only this time obviously I'm going to get all the other pretty little stuff that goes along with that. Okay. So now down here I'm actually going to get the krat. Well, let's go ahead and look at those plots. So there you can see the red line and the 95% confidence bands around the line. And the other thing that I want to draw your attention to is the fact that these are the actual points here, and they don't fit that line particularly well. And that's one of the reasons why I have this column over here that's labeled WT. That's a weighting function. And you'll notice that what it's doing here, and unfortunately in R I don't know clearly yet how to implement this weighting command, but here for small values it's weighted less, and for large values it's weighted less as well. So the largest weighting occurs right here in the middle. So I'd like to figure out how to use that weighting command so that I can apply more importance to the values here that are in the middle of the line, and less importance to these where I know it's going to deviate from that line, but we'll address that perhaps in class. All right, so there is my regression with the data points plotted around it. So this is the Logistic transformation, so the data are transformed here. They're not as you would have plotted them initially. All right, so now I ask for the krat model, so the linear model P prime is a function of distance, and there it is. It gives me the intercept and the slope for distance. I can then ask for the analysis of variance of that, and here I get my ANOVA table, and I can see clearly that the relationship is significant. We could compute the R-square relatively easily, either the R-square or the adjusted R-square. The R-square is going to be simply 11.1813 divided by the sum of 11.1813 and 1.0436, and then the mean square is going to be, or the adjusted R-square is going to be the mean square value right here divided by the total mean square. All right, so now let's use the plot command and see what our plots of residuals look like. And here, as we suspected, here you can see that the fit isn't perfect. So here's our regression line laid over on its side. And then here are our data points. So clearly we're missing something, and that's why we would like to do this weighting to sort of pull this up, pull that up, and then bring this down. Okay. If you look at the QQ plot, it doesn't look all that awful. I mean, clearly we're a little bit off, right? We're down below here and we're up above this. So the slope of the of our points doesn't match the theoretical distribution perfectly. But in terms of what we were trying to accomplish, that is, figure out what the effective area of this is, then there we have it. The next thing to do, I think, with these data, if you really want to understand where that effective distance is instead of plotting p prime against distance, we should plot the probabilities against distance, because here you see the probability is 0.5 when we have a distance of 180 meters. So if you say the area of effect for the kangaroo rats or for the cattle tank is should be where you have a 50% chance of again encountering kangaroo rat mounds, that distance would be 180 meters. So the cattle tank has an area of effect of a circle that has a radius of 180 meters, which turns out to be quite a large area. Very good. See you guys next time.